Okay, so hi again. I would like to say a few words about hypernetwork approach to generative model, and we will start from hypernetworks. Who know what is hypernetworks? Hands up. Okay, so uh, th- the history connected with hypernetworks is connected with general approach to deep learning. So if you have some task, for example, classification task, you need to find three things: the architecture of the neural network which you want to use, which I called F with parameter theta. You need cost function, yeah, so for example, cost entropy, and all you need is to minimize the cost function by gradient descent. And you know, in general, this task is completely solved. Yeah, if you have some classification task, you have enough data, some guy who is able to train the model, architecture are known, cost function are known, everything is okay. And in general, deep learning works in this fashion that we have a lot of data and our gradient descent make a lot of small steps. Yeah, and thanks to it, we are able to find some local minimum. Um, and everything is okay. But we can think about optimization without gradient descent, or in some sense without gradient descent or other optimization like Adam, etc. And in this sense, we can formulate the hypernetworks. So hypernetworks, it consists of two networks. The first one is a hypernetwork, which produce weights directly to another neural network, which we called target network. So in practice, target network is not trained by gradient descent or other optimization, but it takes or gain the weights from a hypernetwork. So hypernetwork produce weights to target network, and target network take this data and solve the problem. And in general, target network is not trained any all because it's take the weights and that's all. And hypernetworks is trained by gradient descent. But you know, it is completely different flow of the training because when you change weight of hypernetwork very slowly by gradient descent, you have a lot of data. You know, the weights of hypernetwork are changed very slowly, but the effect of the neural network, so the weights can drastically change during the process. Is a similar situation like differential equation when you have butterfly effect, where you change the initial state only little, you can obtain the completely different trajectories, yeah, on the end of the differential equation. So in practice, when we optimize hypernetwork weights by gradient descent, we obtain the not gradient-based optimization in target network. Hypernetworks become quite popular in the society, so some of you know what was the hypernetworks. It was quite a simple concept. We have some approach of how to train the hypernetworks, and in general I have many projects with hypernetworks here, hypercrowd, hypershot, hypermum, hypercolor, hypersound. So if you are interested with hyper projects, I always open for some collaboration. Okay, but today I will say about 3D objects. And in general, the main idea of this direction of works is the implicit representation or continuous representation of object. Who know what is implicit representation of object? Okay, some of people know. So in general, we would like to represent classical object. We will use 3D objects, but easier is to describe the idea in the case of images because all the people know what images is. So in general, we would like to represent an image by a neural network. So we train small, fully connected neural network, few layers without any additional I don't know, additional things. And in general, in the case of 2D images, our transformation, our network goes from two-dimensional space the coordinates of the pixel, and goes to the RGB color. And in general, we train our model that if we have the pixel with some coordinates x, y, our neural network produces the RGB color. And we train it point by point, pixels, and in general we obtain the representation of the image by neural network. The shape, color, content of the image is encoded in the neural network weights. And you know, in inference, when we want to render the object or produce the image, you must evaluate your neural network in each pixel to obtain the colors and produce the image pixel by pixel. And in general, the main idea of implicit representation of image was that hyper-resolution. For example, you can train your model on some resolution, and after training, you can ask not only for the integer pixels, but you can ask for many more pixels. The neural network should interpolate it correctly. You can also ask for a pixel which are next to the image and produce something what is next to the main content of the image. But in our case, we use it for 3D objects. So I hope that the implicit representation is quite easy to understand, and you know what it means that we represent the object by neural network. Okay, and we would like to work with 3D objects, and most of the existing method for generative models, most existing generative models for 3D object was constructed by 3D point clouds. Yeah, so we have only points in three-dimensional space. This is an example of the of some architecture. This is autoencoder. We take the 3D point clouds, and you know, 3D point clouds is tricky because you know your neural network should be invariant to permutation, because when you change shuffle the points from 3D point cloud, it's the same 3D point cloud. Yeah? When you have image and you shuffle the pixels, you have noisy image. Yeah. Also, your neural network should be invariant to rotation, because when you take the chair and rotate, it's still a chair. And you take the 3D point clouds into encoder, produce some latent, and produce the decoder. And you know, we have a few neural network which are able to process 3D point cloud. It's called PointNet or PointNet++. In general, this consists of 1D convolution or some attention layer. So it is quite easy to construct. But the bottleneck of such a model is the output, because when we produce the output, our neural network should have the fixed size of output. So we are able to produce the fixed number of points. And this is a problem because, you know, when we train the model, it is quite heavy, and we are not able to use thousands of points for each object. So we usually use 2024 points. So it is not enough to produce real object, because points I plot the points very large, but in general points are small, and you have a lot of empty space in your object. Of course, there is also the problem with reconstruction function, which we are not able to use.
Hey, yeah. Isn't that an issue of the architecture itself? Like if you, for example, had a sequential model that spit out the points instead of trying to like spit all the points at once, then that would be an issue?
You can produce some, I don't know, a network or sequential one, and it solves the problem in some sense, like in natural language processing. But if you want to produce it by autoencoder, GAN, or something like that, it's quite difficult to construct it. It occurs that you are able to use some sequential neural network, but there is a problem with the invariant permutation and rotation, and it's quite hard to train in practice. Most of the existing algorithms use GANs, autoencoder, diffusion models, or something like that.
Maybe what about padding? Can you add like zeros?
Yeah, but of course you can use padding, but you have the upper bound of the number of points. Yeah. And you need to use some reconstruction function, cost function, which is invariant to permutation, half-Earth distance or Earth-mover distance, but this is not important in our case. So to solve this problem, we try to use Hypernetwork. So this is the same as before, but produced by myself. So here we have point cloud, some latent space, we decode the fixed number of points, and the bottleneck of our neural network is the fixed output of points. And the solution is to use Hypernetwork. So the encoder is the same, pointnet or some 1D convolution or something like that. And decoder produced weights to a target network. In our case, target network is a fully connected neural network, similar to this dedicated from images. So it's go from three-dimension x, y, z, the position in the 3D space. In 3D space, so each transfer point by point. I draw the full sample here, but in general it works as an implicit representation, transfer point by point. And here we have a simple fully connected layer with few fully connected network with few layers, 3 to 3, so it's quite simple. And in general, our target network transform uniform distribution on ball on the sphere into surface of the object. In training, we use fixed number of points. So here we have 2,000 points. Reconstruct, produce the waves of target network. We need 2,000 of points, so we run the target network 2,000 times, produce the output of the number, and use the same reconstruction function. But after training, you are able to sample as many points as you need. And in general, you are able to produce quite dense output. And in some sense, it solved the problem with fixed output. But you know, there exist few algorithms which are able to produce not fixed output of the 3D point clouds. But it occurs that our model is in some better because we can use something which we call triangulation trick. You know, if you want to render some object in real world, it is impossible to produce point clouds because point clouds are sparse, in general. So we need to produce meshes, voxels, or some other representation which are easy to render. So it occurs that without any additional information in the training, we don't have any existing mesh.
Yeah, isn't it an issue that each point is sampled independently, that they don't depend on previously sampled points?
In general, the target network try to learn the interaction between points in similar way as in the image. Yeah, in the image, in the pixel is reconstruct or produce independently, and the relation between colors is in the neural network weights. Yeah, and this is the same situation. The shape, in our case, only the shape because we don't have colors, is encoded in the neural network weights. Yeah. So we can use the triangulation trick. So all points from uniform distribution of the ball or uniform distribution on the sphere are inside the sphere. So we take some classical mesh on the sphere and transfer, only the vertex of the mesh or graph, how we called it, by the neural network, and we obtain the point on the surface of the object, and we use the same edges, and we obtain the surface of the object. So our model is able to produce meshes without using any meshes during training. It works because all elements from the ball are inside the ball, so the ball is the border of the ball, and after transformation, the border of the object. And of course, we are able to produce some elements, and it works nice.
So you kind of automatically putting the mesh on the sphere, right?
if you had like a point cloud of like a chair, would it be very tough to put like a mesh on it automatically?
We will try to solve this problem in the next few slides.
Okay.
This is the larger bottleneck of the model that all elements are topological correct with the sphere. So it is quite hard to produce a 3D object with more holes. Yeah, but we solve this problem in the next few slides. At the I can say that our model is generative, so we can produce new elements, some interpolation. You know, this is the autoencoder in general. Okay, so before we go further, I understand that all people know what is GAN and all people know what is autoencoder, but the question is, who know what is a flow generative model? Hands up. Most of people, but I say a few words. In general, flow model is almost the autoencoder, but with the restriction that the encoder is reversed to the decoder. So in general, we have only encoder. This is given by the reverse function of f. Of course, we need to produce the layer which is invertible, and we need to construct in this way that the Jacobian of the transformation is trivial, because we are able to calculate the not elbow, but directly the log likelihood if the transformation is without any bottleneck and is reverse, and the Jacobian is trivial. We are able to calculate the probability of each point. So it is in some sense classical density estimation of the object. One of the most popular continuous normalizing flow, CNF, is a fjord. Who know what is fjord? Okay, so in general, the transformation f is modeled by differential equation. Yeah, so we give the differential equation, and this differential equation give us the transformation from prior, like Gaussian, noise into distribution of data. And this is better than discrete ones, because you know, to model the transformation, you must integrate the dynamic function from 0 to 1. But when you integrate it from 0 to some point, you are able to find the middle stage of the transformation. Yeah. In general, it is quite hard to train this model, but it's very interesting and theoretical background. So I recommend this model for you. In our case, it's quite simple to use. You know, we try to substitute the fully connected function with continual normalizing flow, because in 3D objects in general, people believe there exist many papers that say that flows work better for 3D objects. So we produce almost the same model. We send to this as a the previous work. We produced the continual normalizing flow. Of course, there was a problem. If you have some intuition with maths, you should know that if you calculate the log likelihood function, your prior must be not convex supports, because the zero value of density after logarithm become infinity. So it is not impossible to use the uniform distribution on sphere. So the triangulation trick is hard to use in the case of Gaussian distribution. That's why we try to model own distribution. In general, is a Gaussian distribution on sphere with the parameter of the blur, and we start to training from the quite large sigma, and after the training we have almost zero, but you know the density is not zero everywhere. I don't think it works. And in general, thanks to this modification, we are able to see how Gaussian distribution, universal distribution on the sphere is transformed into 3D object, because we are able to integrate the dynamic function from 0 to 1 in each step. I don't know why it's not maybe. Oh, okay. It's work. Okay, so and it occurs that if you have some background with topology, and the question which was here arises that you know, in general, it should be the connection between prior and the target. They should be the topologically correct, so should have the same number of holes. So if our distribution has one hole and the real 3D scans has also hole, because you know the camera takes the points on the border of the image, our transformation is in some sense correct, because it produces the transformation natural way. And when you use Gaussian distribution, of course, in the case of Gaussian distribution, we are not able to produce meshes, but you are able to train the model. Your Gaussian distribution must be, in some sense, divided into parts, and the center of the Gaussian goes onto the front and the back of the object. So the transformation is more complicated in the case of the log normal distribution and flow model. You are able to produce nice translation between prior and the object. Okay, so we decided we are able to produce nice point clouds, and we are able to produce meshes. So the next step is to produce something more than synthetic data. So we try to produce some real scans. So in general, we take some scan. You know, when you take some 3D point clouds from real scan, you have a lot of missing data. And it occurs that, you know, it is nice to produce the whole chair or whole object. So we decide that, you know, when you see only the part of the object, it is not obvious how the object should be reconstructed. So it is a nice idea to produce many different reconstruction of the existing object. So our model works in this way, that the autoencoder takes only the part of the object, and generative model produces the missing part in many options. In the car dataset is easier to see that we are able to produce hatchback, van, and etc. Thanks to that, we are able to produce many possible reconstruction of object. But it occurs that this is a nice tool and nice feature, but you know, when you produce some reconstruction, it's not obvious that your reconstruction is correct with the environment. For example, the leg of the chairs are too long or too short, and in general, this is a problem. So we decide that that our model should be, I don't know how it's called, be able to adapt to the existing scan. And we use some kind of adversarial example trick that we fix the neural network and move the noise according to some constraints, for example, the distance to the floor. And thanks to it, we are able to modify our 3D point cloud to be consistent with the environment. How the algorithm works, very simple. We have two encoders. One is dedicated for existing part of the object, and the second one is dedicated for the missing part. Of course, during training, we have both parts. On the latent space in the second autoencoder, we use some regularization to force the latent to be as close as possible to Gaussian distribution. We concatenate the representation, and we produce the ways to target network as in the previous models. You know, the first representation and the second representation are completely different. Yeah, but they are concatenated during the decoder into one simple neural network. So the net must concatenate this object in one single consistent object in general. So we take different parts of cars to the one encoder and different parts to the second encoder, and you know, target network is trained only on the existing cars, so it is quite hard to produce the pieces of car which are not consistent. So everything works nice. And in inference time, you know, we take the existing parts, the missing part is missing, so we sample the Gaussian, some sample from the Gaussian distribution, concatenate the representation, and produce the correct point cloud. And of course, we can produce also the mesh of the object. Okay. So now we try to go to the problem with number of holes, so chair, which is not consistent with sphere. So you know, we have point clouds, we have meshes, but there exists another representation, voxels. Who know what is voxel? Okay. So thanks to represent object by voxels, you are able to produce more complicated shapes. So how to work with voxels? We can do it in many ways, but one idea is to use deepSDF. So we sample point inside the object, outside the object, and we train the classifier to distinguish element from the inside of the object and the outside of the object. And the classifier boundary is the shape of the 3D object. Yeah. So in general, we train the classifier to distinguish elements from inside and outside of the object, and the classification border become the mesh of the object. Okay. So there exists some solution which do it. For example, implicit decoder. Here should be the encoder, but the encoder is always the same. We produce the latent representation, concatenate with coordinates of each pixel or voxel, concatenate it, and make some classifier which say we are inside or outside. You know, you need to evaluate the classifier in each point in the 3D grid. Yeah, but this is a classical implicit representation. Of course, problem is that you don't have small neural network dedicated for one single element, like in the Hypernetwork paradigm, but you have a large neural network which is dedicated for all elements. And we decide that we convert into hypernetworks. You know, our autoencoder produces ways to the classifier distinguishes from the inside and outside, and everything works okay. But it occurs that it works okay, but not perfectly. In general, there appear some missing part in the reconstruction. In general, in on some planes, because you know, when you train the classifier, the classification boundary is not smooth. We need some regularization.
Is there any flow in Hypercube or no flow?
No, it's not a flow. It's a classical classifier now. So in the first one was multi-perceptron by reconstruction function regression. Then we have density estimation in flow, and now we have a classifier, classical classifier. And we decide to propagate, to modify the hypernetwork approach, the interval net. You know, here we will have the interval net. I say a few words about interval net, but in general we want to take a cube. So in our case, 3D cube, the voxel, because you know, in general, people think about voxel as a small cubes, but in practice, we use the center of the cube. Yeah, but we try to propagate the cube, and it occurs that exists interval nets. What is interval net? Interval net is a neural network which propagate intervals. In general, you can propagate any dimension intervals. Yeah, in general, it works in the sense that you take on the input neural network the cube, and you propagate the cube by neural network with ReLU activation and fully connected linear affine transformation. The affine transformation of the cube is affine transformation of the cube. You find a convex hull in the shape of cube, and after that you take ReLU and you can propagate it for many layers as you need. And you produce the worst case cross entropy. Worst case cross entropy is a small modification of the cross entropy. The general idea is that it forces the neural network to keep the whole interval on the one side of the classification boundary. So most of cases, interval net are used for some constraints. For example, if you train the model with interval arithmetic or interval net, you know that if some cube is on the correct side of the classification boundary, all element from the inside of the cube are also on the correct boundary of the correct side of the classification border. Okay, so we use the interval net as a target network.
Yeah, just one question. Why do you need can you just make a 3D point cloud and then interpolate between the points? Wouldn't that be easier than?
Of course, you can find many different approaches how to solve the problem. The easiest way is the Gaussian blur. Yeah, you can each point, for example, add the Gaussian blur, and in this sense, your point is not a point but a cloud, and it solves in some sense the problem. But in our opinion, interval net is more, I don't know, mathematically correct, because voxel is a square or cube. So why we need to use point instead cube? Cubes are also nice elements to propagate by the neural network.
Okay.
We didn't verify what happens when you add the Gaussian noise or other rule, but I believe that it works in the same fashion.
Okay, because I'm thinking of this from the point of view of a molecular surface. So when you look at a protein, which is just a 3D structure of some sort, they go exactly the opposite way. They have this information and then they blur it with some sphere to make it.
Yeah, because the problem when you use noise, it is quite nice because you don't have to modify your neural network. Everything works perfect, but you are not sure that it works in the correct way, because when you have a noise, your classification boundary can be, sparse. Yeah, you have the we have the noise, and the classification boundary can work something like that. Yeah, or in different way. In the case of interval, you don't have this kind of problems. Yeah.
Thank you.
But on the other hand, I believe that interval arithmetic is not a nice tool for molecules, because it is a cube. Yeah, but in the case of voxels, it is everything is I believe is correct. Everything works, and we obtain the result we want to get. So we obtain the regularization, and the renders are better in general. Okay. So we are able to work by hypernetworks with 3D point cloud meshes and voxels. But it occurs that another approach is to produce the patches. So we try to produce the fixed number of patches to produce the mesh. And this is also a good idea, but the problem is that the patches are not always stitched correctly, or you have some empty elements in the mesh. So we decided we use the continual representation. If we are able to produce as many points as we need, so we are able to produce as many patches as we need. And in general, we produce the modification which produce as many patches as you need. So if you are able to produce some element on the surface, our model is able to produce the patch here. The modification is quite easy. We have the first stage, and in the second stage, we produce the neural network which propagate patch to the surface of the object, because we have the parameterization of the object is quite easy to produce. And in consequence, we are able to produce the new version of Atlas Net, and we don't have any artifacts with holes in general, because if some patch is too large and produce some artifacts, you can delete it and produce many small patches, to fix the problem. Of course, we have also constraint. We just connected that we need a lot of patches, so this is the limitation.
I was just wondering what's the rationale of like even trying to use patches instead of just perturbing the sphere, the mesh that you had before. So why did you decide to try this approach?
Yes, in general, it works. It is quite hard to. It is quite hard to plot it here, but in general, it works in this sense that this patch goes here on the sphere, and the patch from the sphere goes here to the. So the idea is exactly correct with the idea, but it is quite hard to plot. Yeah, but the idea is in this sense. Yeah, we have this transformation, and in general, the idea is to take the patch to the sphere, from the sphere to the 3D object, which is present here in some sense. Okay, so we decide that we are able to produce meshes, voxels, everything is okay, but you know, we don't have colors. In general, colors are quite important, so we decide that we should be able to produce color for our meshes. Here you see some examples of meshes with colors. The idea was very simple. You know, if you are able to produce points, you should be able to produce color for the points. Points are converted to the mesh, so you can give the nodes of the mesh with the colors, and the colors of the face is produced by gradient from nodes. And the idea is quite simple. We have the first stage, which is a point cloud, and goes through the autoencoder to the target network, which transfers 3D point clouds to the object. We train the second autoencoder, which takes the 3D object with colors and produce colors. And you know, in general, here we have point cloud with colors, but shape is encoded here, so the second neural network learn only the color. Yeah, it's tricky. And in general, here we have the Gaussian regularization, so we can generate many different objects and many different colors for the object. The idea is quite simple. If you train it, which is very simple, you have transformation point sample from prior goes to the point cloud gets colors. So you take the mesh on the sphere goes on the surface of the object goes to the surface of the object with colors, but colors are dedicated only for nodes, not for the surface. Surface are color of the surface is produced by a simple gradient between colors of triangulation. And you know, we obtained some object which was in general with colors. And you know, this object has a lot of problems. The easiest way is to see that when you have the border between glass and the rest of the car, it's blur, because you know we mark only the face of the object. But still, it was, I believe, years or 2 years ago, the SOTA. And you know, in general, it is a problem to generate colors for mesh and 3D object. But everything was completely changed when the neural network fields was produced. Who know what is neural nerve? What is radiance fields, neural radiance fields nerves? Okay, so few people know. So in general, there's new idea to producing 3D object. And you know, in natural language processing, we have ChatGPT. Yeah, in the images, we have diffusion. And these two models change the area completely. And in 3D object, nerves do the same. I know that 3D object or the area of 3D object is not as popular as natural language processing or image generation, but in the case of 3D object, it was completely changed. So the idea is quite simple. Yeah? We do not produce the object full object. We produce only this part of object which we're looking at now. Yeah, so for example, if you look on me, nerve produces only my face and my back does not exist. Yeah, if I turn off, yeah, the neural network produces what you should to see. How to train it? We take a lot of, I believe, approximately 100 images of the 3D object. We need the position of the camera. And we train our neural network to produce novel views. So if you put a new position of the camera, neural network should produce you the new view. Yeah, it should be work very fast. So instead of producing full 3D object with meshes, patches, voxels, you produce only the view you need in some situation. You give the position of the camera, and the neural network produce the novel view. And in general, it works perfectly. Yeah, yeah. We can show some examples. Yeah, it work? Maybe it's not work, but in general, but in general, the idea is that a nerve is a fully connected neural network produced in similar way as implicit representation for image and implicit representation for 3D object. And you know, amazing is that you have fully connected layer with fully connected neural network with 8 layer, and you are able to produce high quality images. I hope it and I show you later, maybe. Okay, you must trust me that it works nice. So what is the idea? Idea is quite simple. Yeah, I know, but okay. So we are able to produce high quality 3D object, yeah, with color, automatically with the colors. So okay. So nerve solved the problem with colors, solved the problem with representation, because we don't have any representation, we produce only the image you see. Okay, so the idea is simple. You have the simple fully connected neural network perceptron, multi-perceptron. You take 3 coordinates of the point and the position of the camera, which is parameterized by 2 elements. So in general, you take the point of the camera and the position on each point in 3D space. So our MLP goes from 5-dimensional space into 4-dimensional space. We produce RGB color, and sigma is the density of the voxel of the point, so how it's transparent or how it exists. Yeah, if sigma is 0, the point does not exist, and you know it's completely transparent. And you know the magic is in the training.
So is the point to replace ray tracing?
Yes, it's the idea of ray tracing. Yeah. Okay. In general, the nerve is the idea of ray tracing. So in general, your nerve take the position of the in the 3D space and produce the color and the density of this point. And during training, you take the position of the camera, produce the ray. The ray goes to the image, to the some pixel, and the color of this pixel is the reference color. And then you sample points on the ray. You should to integrate some but in the easiest way to describe it, you sum all elements of the array. So on each point you produce RGB and sigma, sum all elements on the array, so aggregate the information, and you train the model that the aggregated information on the array should be as close as possible to the color of the pixel which you go through. Yeah, and this is the MS loss. And when you finish your training and you want to produce a novel view, I know that it's not novel view, but we assume that it's novel view. So to produce novel view, you take the position of the camera and produce a ray through each of the pixel, and you know, go from the pixel, sample point on the ray, aggregate the information, and the aggregated information you put on the image. Because it was trained in this fashion, yeah, you are able to produce the correct view. Why it works? it works because during the training, the eye are very close to each other. Yeah. So the implicit representation nerve must to produce consistent representation. Yeah. And thanks to this consistent representation, you are able to produce novel views. And everything is inside small, fully connected MLP neural networks. Yeah. Okay. So if people find nerves, we decided nerves perfectly suit for our framework with hypernetworks. Yeah, so we decide we must to use nerve in our work. So the first idea was, all people transfer existing views to the nerve which produce new views. And we decided we're working with point cloud, so maybe it is possible to transfer point cloud to the nerve. So the idea was quite simple. The first idea that we produce the right which goes only for existing points. If right now don't have any connection with some existing point, we find the nearest neighbors. We use nearest classifier to find the nearest point and try to train the model. The model is trained directly on only one object. It occurs that it is almost impossible because the point cloud representation is extremely sparse. If you have the point of willow or the glass, you have only few points, and the model is not able to learn how the car looks like from the point clouds. And it was blurry. So we decided we need to produce the generative model. In the first approach, we use autoencoder. So the idea was to do the autoencoder, we put the point cloud with colors. It goes through encoder, and the coder produces the target network. And here we have flow, classifier, and interval net. Why not to use the nerve? So, and it occurs that it works nice. Yeah, in general, the framework is quite easy, and we are able to produce some object which are dramatically better than elements which are produced by meshes. But still, it's not high level. Yeah. In general, when you train nerve on a single object, you have extremely sharp object. When you train the generative model, which must to generalize and train on many different objects, the quality of this render is not enough. So we decide that what is the reason of the problem. So we decide that the problem is the autoencoder. Autoencoder in general produce the blurry images. So we decided we need to produce a GAN. Yeah, and the idea of GAN is also quite simple. We take the Gaussian noise. Gaussian noise goes by a generator to produce target network. Target network is a nerve. So we are able to produce any possible view. So we sample some possible view. So we try to use the discriminator which is dedicated not for 3D object, but only for images. So we sample only one view, which goes to the discriminator. Then discriminator is directly taken from the style gun, and it works perfectly. So and it occurs that then that GAN are able to produce better renders, and we are able to model glasses and small pieces of the elements. Maybe here is more example. So in general, it occurs that it produces. We believe that it produces the correct renders, which can be used in some application. And we decide that it is nice that our framework can be used in nerve associative. And we decided that if we are able to produce cars, planes or chairs, so what next? And we decided that the next is to produce faces. In generative models, it occurs that, producing faces is easier than producing cars or something like that, because all faces are similar. Yeah, and in general, it's quite easy task. But in 3D object rendering, it is not as easy task, because we want to produce faces which we want to animate. Yeah, so we decide that you know, that we combine existing method which work on meshes with nerves. And you know, this is a flame model. Who know what is flame model? One. Okay, so flame model is a quite old model. It is produced by, it is not the deep neural network, it is a classical linear model. In general, we have the mesh of the face with 2000 nodes, and where we have linear relation between some features, and when you change some feature, they are dedicated to the you know, open mouth or shaking your hands or appearance on the face. Yeah? Most of the existing solution which fit your body or face in some games or something like that works by flame. The solution is quite easy. When you have the scan of your face, you find the landmarks and move our attributes in such a way that the mean square error between the point of our face and the point of the flame are correct, and it worked perfectly. And you know, this module is able to animate our face. So we try to use it in nerve, because animation of mesh is easy, because this is the point in 3D space and you can move them. But if you represent the object by neural network, implicit representation, it is not obvious how to force the neural network to move your mouth or other elements, because everything about the objects inside the ways of the object. So in general, this is a problem to control nerve. Yeah? In general, if you train nerve only on a single object, it is especially hard, because if you have the generative model, you know, you can do some magic in latent space or something like that. So we try to train nerve frame, which is a mixture of explicit and implicit representation. So we have neural network nerve which produce RGB for each color. So the idea is the same like nerve. We take the position of the camera, produce the ray, sample points of the ray, and on each sample we need to produce RGB color and density. But RGB color is produced by our nerve model, and the density is arbitrarily given by the mesh, by the distance to the mesh. So we calculate the distance to the mesh of the point. We use some activation function which gives non-zero element in the epsilon neighborhood of the object. So if element is in a small neighborhood of the mesh, we produce nerve can produce RGB color. But if the point is far from the mesh, we arbitrarily give 0, and we start to training. And you know, nerve try to produce consistent representation. So if nerve wants to put some color in some place, we must to move the mesh to the place where the nerve wants to put the color. And it works in the sense that it simultaneously train the mesh and simultaneously train the RGB color. And when we finish our training, we obtain a model which is able to produce novel views. Yeah, but if we take the flame which is inside the object and move, I don't know, some parts of the mesh, our model must to move the consistent, because you know the pixel does not exist, so it all disappear. Yeah. So thanks to it, we are able to train our model on a single face and animate the object. Of course, we still have some problems with that because the quality of the render is not as good as in classical nerve, and we try to find with that. But I believe that we are very close to the final solution. Okay, so we can go to the end. You know, so the problem with the nerve flame is that we train it only on the one face. Yeah, to be able to manipulate the face, we believe that the model should to see many different faces, many different mimics or expressions, to learn how to modify it. So, what is the solution? There are many possible solutions. The easiest one is to produce GAN or autoencoder and train everything together, and we try to do it also. But better idea is to force the small neural network to be able to generalize. Yeah? So to take simple nerve and train it in some sense that it is able to produce many different faces, not only one object. And you know, people also trying to do it. So in general, there appear many versions of nerve. The first version is the original version, where we encode the structure of the 3D object in the ways of the MLP function or neural network. Other approach is to produce the voxel representation, which is trainable. So we train the color which are inside in each voxels, and use only small implicit decoder to aggregate the information from the voxel and produce renders. And it works better because, you know, voxel is better representation for 3D object than the weights of the neural network. Then people use triplane. Triplane is better than voxel because we can produce triplanes by classical GANs, because GANs are able, or other generative models, because they are able to produce images. And the idea is the same. So if we predict the color and density for some picture, we apply the projection on 3D planes, aggregate the information, and go through the small implicit decoder. And we think, or we try to produce the model which use non-trainable representation. So during training, we have the number of existing images. So we divide the number into two parts, 50 to 50, and some of the parts are used for training and other for representation. So we have fixed images, and our idea is to, when you have the eye, sample some points. So if you have some points, instead of taking X, Y, Z and produce RGB color, we project this point on each of the plane, aggregate the colors from the planes, and produce RGB and sigma. And it occurs that this model is able to generalize in some sense.
Sorry, could you maybe just explain the last slide a bit more? I don't think I fully got it. Yeah, this one, thank you.
So in general, maybe. Okay, so in general, we have classical nerve, and you need to predict the value RGB and sigma for each point on the eye. So in classical model is that you take the point here, you take the coordinates X, Y, Z, and the position of the camera, and it goes to the neural network. And in our model, this point is projected on the existing images. Yeah, and when we project the elements on the existing images, we take the color of the pixel here, here, and here, because you know, when you see the object from different position, we as humans, we are able to produce everything else too. So all these colors goes to the implicit decoder, produce density and RGB color. Yeah, this is the idea. And it occurs that it works in some sense. We produce, here is the effect of the multiplane nerve. And you know, we have autoencoder in our in the renders are better than our autoencoder in some sense. Of course, we are not better than GAN. Yeah, but still, our model is very small. Yeah, so our model has similar architecture to a classical nerve, which is dedicated to one object, and our model is similar, even less trainable parameters, and is able to generalize in some sense. Of course, the work is in the middle stage because it is not enough to say that it's generalized correctly and produces new views, but it works better than autoencoder. So we believe that we are able to produce something more. Okay, and in general, this is all of my talk. But yesterday I say about a few projects which we tried to start, and now I can say something more about the project because I think you understand how they work. This is our project, and you know. The first idea is simple. We would like to use the same model like in faces for hands. In general, when you have a VR representation, I hope you are familiar with it, you see only the mesh of your hands or even less than the mesh of your hands. Yeah? So we can use the existing representation, combine it with nerves, and produce real-world hands in general. And we believe that this is quite easy project. But we already started. We rather find the data set, and we try to produce the modification. The second idea is, you know, the gun which I talk about. It works on cars, yeah, chairs and planes. But we would like to force it to work on faces, and the idea is that we here put the flame. Of course, the flame in the sense of the parameters which we describe the flames, and put them to the generator and on the input to the target network. And we believe that thanks to this conditioning, we are able to produce human faces which can be animated and also has better reconstruction than the previous model. This is the idea of multiplane nerve. I say that it's generalized in some sense, but not on the level similar to the gun. So the idea is that maybe instead taking only one color from the projection, we can take patch and use some architecture which is strong. In our approach, we try to use a vision transformer. Yeah, that's the idea to force it to working. And of course, with 3D object, we do a lot of different things. So we think that this is the moment where to start with some other data, and we believe that video is almost 3D object. Yeah, in the sense that the number of frames is the third dimension. Yeah, and we also try to start with some project. We are on the beginning with either we have some idea to produce some trajectory which goes through the image and apply the relation between images, because in most cases people produce the implicit representation independent for each target. Okay, and that's all for me. Thank you for your attention.
We have like a bit time, like two last questions, okay?
So I have two questions. The first is, what kinds of metrics do you use to quantify this? Because I mean, most of the things you showed were visual representation, which is good, but is there some number that I can put to these images?
Yeah, of course. There are many methods which are dedicated for 3D object and for nerve representation. In general, you divide your scene in training views and evaluating views and testing views, and you can calculate some mean square error or other representation, other numbers. So there exist many measures which describe the quality of the renders. But I as you see, I don't like the numbers in general, because if you want to know which model has the highest numbers, you can open the all new paper has better numbers than the previous.
Right, thank you. And my second question is, can you use like these softwares that make games? For example, games have really realistic 3D images, like 3D.
Yes. Nowadays, nerves become very popular, and the main problem is how to mix the mesh representation with implicit representation. Because some part of the object is a simple mesh, and you use ray tracing to produce the view, and some part is produced by nerves. But there appears some software for it, and I believe that next to few years, all representation in games will beat the nerve.
Right, thank you. Very cool. Thank you.
Another quick question. Okay.
I would also be interested in the beginning. You showed like this hypernetwork to kind of reconstruct like an object. For me, it feels like a variational autoencoder with extra steps. You could like just add like a residual connection, and then you would combine like the residual over like the latent space with the activations, and might be similar to kind of having like the image fed in with the weights. So for me, it's like, okay, I changed a bit of the architecture, and it's actually still producing reasonable results. So did you kind of compare these results to state of the art? Like, did it improve, or was it like not much worse, or was it just a little bit worse? Or
in general, there is because this is a question why implicit representation is nice in general, in the simplest word. And you always are able to produce some GAN on diffusion model which encode a lot of objects and produce as many objects as you want. But this is a huge neural network, and we try to produce a small neural network which is dedicated only for one element, and you can use them for mobile phones or some other elements. So you can produce this part, the implicit representation, and take only this element. So you don't need architecture. You can take it and put somewhere. Yeah, and I believe that the second answer is that for humans, the structure of the image is natural, yeah, because similar colors are each other in general, yeah. We produce RGB to be as close as possible to how our eyes work, yeah. But it is not obvious that for neural networks is the best representation. Maybe the weight of the implicit representation is a better idea. Yeah, of course there exists other possible answer for this question, but I believe that's too.
okay, so the core idea is like knowledge distillation, basically, from like a general model to like a specific domain task. Did you compare it to like other ways of distillation with similar size?
Of course, the implicit representation is in general a nice solution, but we can produce implicit representation in many ways. Hypernetwork is not the only solution. I like hypernetworks, and I present you the hypernetworks, but there exist other solution which works by conditioning. Yeah? So in general, you have a little bit larger neural network here, and your model produces some conditioning for it, which you add on each layer or something like that, and you are able to obtain the also implicit representation, but in a different way. Yeah? So this solution exists, and no one knows which is better because they give similar results. Yeah.
Okay, thank you very much. Very interesting talk.
Hi, thank you for the ultra nice presentation. There were two ideas that caught my attention, and I would like a little bit more information about it. They were from the start of the presentation. The first was this autoencoder architecture with flow something like that. No, the one with that you parameterize the encoding as a dynamical system, and you evolve it. Yes, this is an incredibly interesting idea. You mentioned that it was very difficult to train, and well, especially I think the nice part is that it's invertible. I guess my question is, how does this architecture or this approach compares to some other invertible architectures or approaches, which I think come with a lot of computational cost and constraints to your parameters. Like, how practical is this to use?
The answer is quite simple because it depends on the application. The model, the continual normalizing flows, are good in lower dimension. It is quite hard to train this model or celeb A, HiQ or something like that because the space here is large, and it's not trivial to train. I believe that no one is able to do it. But in the case on small dimensions like 3D objects, yeah, it is the best solution because it is able to learn any possible distribution. Yeah, it's a universal approximator because we are able to use log likelihoods. So if you work in relatively low dimension, the FFURL is the best solution. If you go with dimension higher, the better solution is to use diffusions or something like that.
So in your case, it's low dimensional because you actually learn flows in 3 dimensions only, and then you evolve points.
Yeah, dedicated for only one object. Yeah, my flow is we generate one flow for one object, okay, and the structure of all objects are in the autoencoder, which is a classical neural network.
Ultra interesting. And then the other question that I had was about this hyper network architecture. From my probably bad intuition, I will say that taking large steps in the parameter space is actually a bad idea, and this is this is why we use learning rates that are small, because we want to be conservative in how much we actually are changing. So gradient-based optimization actually allow us to do this down value path. But then you mentioned that these architectures are good because you can actually take large jumps in parameter space. Can you elaborate a little bit about this?
So it also depends, but in general, the idea is quite simple. That hypernetwork is a neural network which see whole world. In general, a lot of elements of the training data set. And the target network is dedicated only for a small task. And the idea is that we are able very quickly produce some neural network dedicated. If you watch that Terminator, you watch that Terminator, you have Skynet. Hypernetwork is a Skynet, and produce many small AI models, for example, Arnold Schwarzenegger to kill Sarah Connor, but also can produce other elements to solve other problems. Yeah. So in general, the idea is that hypernetwork must be able to produce many different elements. Yeah, and that's why we need the large
So in this case, like the hypernetwork will actually be producing the implicit representation for that image, for example.
Yeah, but you know, hypernetworks can be used for continual learning, fusion learning. So some neural network is dedicated for some task or for a small task. The application 3D object is nice for me, but in general, you can use it for many different approaches. Yeah, you can always use hypernetwork if you have many different small tasks in some sense, and you try to produce something what is dedicated for this small task. In our case, the small task is the implicit representation of 3D object video, but the small task can be in fusion learning, aggregate information from support set and solve or in continual learning when we take the embedding of the task and produce something dedicated for the task.
I have a shit ton of questions, but probably I will
Sorry,
try to...
I have to stop you here. So excellent results, Przemysław. Thank you for the talks, for the spontaneous talk. So the last actually point on our agenda is day lunch in 4 minutes, and I have like small request that we have to leave this room because that's gonna be another event happening this afternoon. So take your belongings and see each other in lunch. And if you want to talk about hypernetwork to Nerve, find Przemek or any other organizer during lunchtime. Thank you.